Hi everyone, I hope you had a nice spring break despite what's currently going on. Hopefully you did something fun though, maybe playing video games, watching TV, studying, or maybe even playing board games. Something that you can do at home where you can stay safe. So today I'm back with another lecture, lecture 10, where I will talk about different weight initialization schemes and also tricks that can help you with making deep neural networks learn faster and better. The goal for me today, though, is to just reduce my number of ums, because you have probably noticed in the last lecture I need some more practice with recording, but yeah, practice takes time, so this time I try to do a better job with that. It's also new, uncharted territory for me, and what I also found out is actually recording is not as easy as it looks like. I mean, now I really appreciate all the efforts that go into YouTube videos. So the first topic we'll talk about today is input normalization, different ways to normalize data inputs to our neural network. And then I will show you some weight initialization schemes and also one common popular technique called batch normalization, which is one of the major techniques or tricks in deep learning that help with training faster and better convergence. So let's get started. Let me do the screen swapping as usual and get started. Okay, let's talk about feature normalization and weight initialization. There are two topics today that we will cover one by one. And like always, you can find the slides on GitHub here under this link. You can download the slides before you watch the video, so you can take notes on your slides as usual. So the first part of today's lecture will be on feature and input normalization. There are multiple techniques for this. There's batch normalization, instance normalization, group normalization, layer normalization, and so forth. And why we care about this is that these are methods that can help us training deep neural networks more, I would say, efficiently. So using these techniques, we usually need fewer iterations to converge, but also it helps convergence. Usually it can also help generalization performance, and it also really helps with really deep neural networks. Because like we talked about in previous lectures, if we make very deep neural networks, one problem is exploding gradients and another one is the vanishing gradient problem. And clever normalization techniques can help a little bit with that. The focus, though, will be on one particular technique, which is batch normalization. This is really the most popular ones, and there will only be one slide on the other three. They are kind of related, and we will revisit them later when we talk about convolutional neural networks in a future lecture. Another trick, so I would both consider both feature normalization and weight initialization as tricks. The other trick is weight initialization. So in feature and input normalization, so the first topic, we'll talk about ways we can scale the inputs to the layers in the network. So that could be the inputs to the first layer, but also the inputs to all the other hidden layers in the network. Weight initialization, this is closely related to normalizing the inputs. However, this has something to do with initializing the starting weights for our network. They are also important, of course, for eventually convergence. So choosing good starting weights it's kind of crucial in PyTorch. You kind of didn't notice this because PyTorch already uses a clever weight initialization scheme for you by default. So by default, you don't have to worry about that. I can remember I asked you a question once. Why is it important to normalize or choose small random weights? When we had a neural network that had multiple layers, let's say something like this. Again, everything is connected to everything. It's always a little bit tedious to draw all these little connections here, but you know what I mean. So imagine you have a network where everything is connected to everything. You have multiple layers and you initialize the weights. I asked you, why don't we want to have the same weight for every neuron here? So why has every neuron, so these are maybe the, let's call them the inputs, and each of these inputs, we should maybe use a color, That is a little bit different. So I have a W1 that connects the first unit in the first layer to the first unit in the second layer. Then I have a W2 that connects the first unit in this layer to the second unit in this layer, and so forth. So for every neuron in a previous layer, this is why it's called a fully connected network, the inputs are connected to every unit in the next layer. And if we would choose the same weights, so if we all initialize all the weights to 0, what will happen is that really each neuron in the next layer here, let's color them all pink, so let's call them hidden layer 1. All the units here would essentially have the same value if all the weights are the same, because if W1 and W2 are the same and they are both coming from this neuron, then of course this neuron and this neuron will also receive the same values, and this is true for every neuron. So if we don't choose different weights, all the values will be the same, and then there's really no, this will be the same as having just a linear combination of these features. So you can think of it as just scaling this by a constant. And then we really use all the advantages we have when we use multi-layer perceptrons. So in that way, we want to use non-symmetric weight initialization scheme. So we can initialize the weights to small random numbers, and that would solve the problem by breaking this symmetry. Why is it not enough to initialize weights to small random numbers? This is all what these other techniques are about. But they add some certain tricks to this to be a little bit smarter about that, not just using, let's say, small random numbers from normal distribution, but also considering the number of inputs and the number of units in the hidden layer. So there are some additional considerations to consider when initializing weights, and this is something we will talk more about in this second part. After we covered both these topics, these tricks for making deep neural network training more efficient from an optimization perspective by feature and weight initialization, there's another big category of tricks that we will also talk about in this class, and this is what we will talk about next lecture. This is focusing on the optimization algorithms themselves. So the topics we talk about today, of course, also influence the optimization, but here we will talk about the optimization algorithm directly. In particular, these are, I would maybe call them advanced stochastic gradient descent based algorithms. So these are modifications to stochastic gradient descent that can help us also to learn more efficiently. Usually in practice, you may ask, what kind of trick shall I use? Usually for these, they are kind of additive. So usually you use multiple of these, not only one of these. So usually, you use multiple of them at once. And different deep learning frameworks, they also choose different options for you by default. Something like batch norm is something you always have to explicitly add, but the weight initialization schemes is usually, one of them is usually chosen for you by default by the deep learning framework, whether you use TensorFlow or PyTorch. Which one, it kind of depends also on the version and what kinds of layers you use. We will talk more about this later. By default, usually we used vanilla SGD, which has some advantages as an optimization algorithm. But there are studies showing basically that SGD is can result in better generalization performance, but it's also a little bit trickier to train. So most of the time, what I use, or what most people use, is Adam. But again, I will cover this a little bit more in detail later. So before I get distracted on this singular slide here, let us really dive into part one, and then we can talk about one thing at a time. So the first part is input normalization, normalizing the inputs to the network, but also this term implies that we also talk about inputs to any hidden layer. So it could also be the inputs to a hidden layer and inputs to a first and second and third hidden layer. So the inputs to a hidden layer are the activations. So we are talking about here about layer inputs. So why do we care about normalizing inputs. And this has something to do with the fact that we are also using gradient descent or stochastic gradient descent. So imagine we have a loss function again, or like always. We have the surface plot that I've shown you several times in different flavors. So in the surface plot here, this is a depiction of my loss function. And the loss minimum is here the center of this surface plot. And the further away I'm from this plot, so these contours are highlighting the distance, so the magnitude of the loss. So the closer to the center, the better. And each contour is a fixed constant value that is, let's say, let us maybe put some numbers here to make this more clear. So let's say this is at this contour line we have a loss of 10, here we have a loss of 20, maybe here 30, and here 40. And you can think of it as mean squared error loss, for example. And here this would be my zero loss. And this is just the loss surface of a convex cost function. Here we just, for example, assume this is MSE. On the axes, I have W1 and W2. These are two parameters of a generalized linear model. So just the whole general concept applies to kind of any type of architecture, but since I've drawing here these concentric circles, they belong to a convex cost function. So in that case, you can think of it as, let's say, linear regression. So let's say you have this linear regression neuron, and let's do it like this. We only have two weights, W1, W2, and then our bias unit, and then our output. So I'm showing you here the weights W1 and W2, and of course what we want is finding weights such that when we compute the prediction over the training set, so when we compute the MSE for the whole training set, which is like this, so we have y minus y hat, say I, here's an I, and then squared. So assume we have this mean squared error and we want to minimize this. We want to find the weights such that this function is minimized, which is the center here. If now these weights are, if the inputs are different magnitudes. So for instance, let's say for one weight I have, let me think about something. Let's say age and salary. So for one weight I have, or for x1, the input range is, what can be the age? I think no one can be negative years old, but let's say just something between 100 and 120. This is my age. And for x2 I have the salary, which could be, let's say, measured in dollars, could be between $0 and pretty large sum, I don't know, but let's just say 10 million per year. This is a little bit extreme, but maybe, yeah, I mean, I guess such people exist. So if I have inputs that are very large and some inputs that are very small, depending, let's say both weights have the same influence on the decision or on the prediction. And if I have values that are large and small, the weights will also be naturally small and large. Usually, let's say if both features are equally important, I will have a relatively large weight for this one and a relatively small weight for this feature. That means by making a very small change to, so a small change here has a larger influence on x1. Small change, let's say, of a value of 10 or 10 years has a larger influence than a change $10 in x2. So the weights kind of reflect that. So for one you have a naturally larger set of weight, or larger weight. For the other one you have a smaller weight. But then usually you choose the learning rate for all the weights. So when you use your gradient descent, when you update a weight, you write the wj, which is the updated one, let's say at t plus 1 time point t, and this is the previous weight at time point t, minus, so basically the negative gradient times the learning rate. So let's say we call the learning rate eta, and then the partial derivative of the loss with respect to that weight. Yeah, so usually we use the same learning rate for all the weights. So if we want to, the problem now is if we have large and small weights, it's kind of hard to find a good learning rate that works well for both weights. So in that way, it's really hard to train a network where you have inputs on different magnitudes. So you will have something like where you go into one direction a little bit more than the other. So again, this is also stochastic gradient descent, so you don't make steps perfectly perpendicular to the surface, but you have some small noise. And then also due to the noise and also due to the learning rate, it's really hard to learn with inputs on a rather different scale. So what you see here is that this is really exaggerated, but it can happen that you have a lot of wasteful updates. So you don't really go very efficiently towards the minimum. And this is why we usually want to normalize the weights. So if you normalize the weights, you have them approximately on the same scale, then your loss, I'm just making some space here. So your loss, oh, it's a little bit lagging behind. The loss will be more circular, more symmetric if the weights and the inputs are on the same scale. And that really helps with the optimization. So again, this is exaggerated. Oh, I hate this word. Exaggerated. So you have a more efficient update here at the bottom. You need fewer steps towards the global minimum. This can be, for example, achieved by just standardizing the input features. So this is in a single layer neural network like linear regression or logistic regression. So the standardization that we have used before is simply, what we simply do is we subtract the training set mean for a given feature. So J is the feature index, so the jth feature. So we subtract the mean and divide by the standard deviation. As a consequence, the new mean will be 0, and we will have unit variance and standard deviation of 1 then also. And yeah, this is one common way of standardizing features. And also what will happen is, as a consequence of that, that the values are centered at 0, and we have positive and negative values as inputs, which is also helpful for the optimization algorithms. Similarly, the weights are usually initialized that they are also centered at 0. So what I'm just showing you here is really like I was drawing here for the linear regression model. What I was showing you here applies to generalized linear model. So what happens now if we have a network with multiple layers? So if we have a network with multiple layers, I have to connect everything again here. That's so much fun always. Okay, so this is my multi-layer neural network where almost everything is connected. I was a little bit lazy here, but you know what I mean. So in my fully connected layer network, I have in the first layer, assume I have standardized my features using the approach I showed you in the previous slide. This happens for the first layer, but now what happens here? So depending on what activation function I use, I won't have these standardized or these same properties with mean centering. For example, if you think back of the logistic sigmoid function, which was something like, or exactly like that, where z is your net input, what will happen is that the values will be now between, so the input values are minus infinity to infinity, and the outputs are between different color, between 0 and 1 with 0.5 in the center here. So what will happen is now that the values are not mean-centered anymore, zero-centered anymore. They are all positive values, so they are now different. And also, we could we can standardize again here. For example, we can standardize these activations again here, such when they go. Let's make a few more layers. If they go, if the next layer receives these as input, then that we have again mean centering and unit variance. The only problem with that is we would kind of lose all information. If we always standardize, then no matter what we do with the inputs, it will always be the same in the hidden layer. We will always have the same values there, whether we have very large inputs or very small inputs, and this doesn't make sense, right? So we shouldn't always have the same values here, whether or not we receive certain data points. So what we need something more clever. We need something that kind of learns from the training data also, where we have some parameters. And this technique is called batch normalization, which is almost old in the history of modern deep learning. It's already 5 years old by now, but it's still very, very popular and commonly used. And there are also many meta papers which study why batch normalization works. There are some theories why batch normalization works. The first theory was in this original paper, where they hypothesized that it reduces internal covariate shift, and we will revisit what that means exactly after I outline the procedure of how batch normalization works. So yeah, batch normalization, the brief outline is it's a method that normalizes hidden layer inputs. So it applies to every hidden layer where we add batch normalization. We don't have to add batch normalization to every layer, but we could. It helps primarily with exploding and vanishing gradient problems. So there are some papers saying that it helps with that, but also there was recently a paper showing that it actually causes exploding gradients. So it's a little bit controversial. It can also increase training stability, and this is maybe the most notable features when you train your networks. You will find that using batch normalization will help the network to learn faster. So you need fewer epochs, but also you can often reach better generalization performance. You can think of it simply as an additional layer. So you can think it can be understood as an additional normalization layer. It's normalization method, but it's also, you can think of it as a layer in the network because it has also its own parameters that have to be learned using stochastic gradient descent or any gradient descent method based on backpropagation. So there are additional parameters when you use batch normalization. So to explain what batch normalization is, let us go through this one by one. So this is multi-layer perceptron you have seen in previous lectures. It was a lot of work making this here in Keynote to draw this one, so I like to recycle this figure. So what you have here is a multi-layer perceptron with 2 hidden layers and 1 output layer. So this is hidden layer 1, hidden layer 2, the output layer, and the input layer. So here, this is our loss function. It does not really matter what kind of loss function this is. It could be mean squared error, cross entropy. Does not really matter. The only thing that matters is that we have a loss function here. So suppose we have now a net input, so in the second hidden layer. So the superscript here denotes the layer index of the hidden layers. So the first hidden layer here has the index 1 and the second hidden layer has the index 2. So Z1, this one here, Z1 superscript 2 would be the input to the second hidden layer. So this is a net input that is computed by applying the weights that are connecting hidden layer 1 and hidden layer 2, and like we've done it many times, we compute the hidden activations by, so if these are matrices, let's just maybe think of it as vectors for now. If everything is concatenated, I mean, it does not really matter. Let's think of it as vectors. So we computed this many times. This is the net input by computing the weighted inputs and then adding the bias. And if we have, so this applies for the net inputs in the first hidden layer. If we have the second hidden layer, this x, so if we compute the Z2, this x becomes the activation of the previous layer. So if this is now Z2, then this x becomes the activation of the previous hidden layer. So suppose we have this net input that is associated with the second hidden layer. I was just outlining the terminology here because I know I'm usually using too much space on each slide, so I was trying to separate out these slides. So just keep everything I said in mind. Now consider the examples, so the training examples in a given mini-batch, such that the net input of a given training example is written as this one. So this is if you have training examples 1 to n in a mini-batch. This is your mini-batch size. So here n is the mini-batch size. So assume then you have an arbitrary training example or arbitrary index to a training example in this mini-batch, index I. So assume now this is the activation net input associated with this particular training example. You can't really see this in the network because in the network what we have is we have something just for, let's say, one training example. So we have just a general concept of where the net input is, but we don't have the different training examples shown here. Here the figure just applies, let's say, to one training example. But now let's assume we have computed this value here for each training example in the mini-batch. So I is the index for the given training example. Because it's getting a little bit crowded here with all these indexes, so we have already 2 superscripts here. So like I'm saying here in the next slides, I'm just omitting the layer index because the concept is also super general. It applies to any hidden layer. So let's just talk about a hidden layer, not about a specific one. So let's just not worry about the layer index for now because it's a very general method. But if you want, you can just think of it that there is a superscript with the layer index. So now I'm going to show you all the steps in batch normalization. Actually, there are only 2 major steps, so it's super simple. It may look complicated at first, but really it is a very simple method. Okay, so the first step is normalizing the net inputs. So this is exactly the same as something you've done before, namely z-score standardization. Okay, I'm running out of space. Okay, z-score standardization. So first what we do is we compute the sample mean of all the examples or the net inputs in the mini batch. So again, n is the mini batch size. Then we compute the variance of all the net inputs in the mini batch. And this is something we do for every layer separately. Again, like I said, let's not worry about different hidden layers. Just assume this is for a hidden layer. We would repeat the procedure for every hidden layer. So first we compute the mean. And then we compute the variance. And although it's a sample variance here, we don't use the Bessel's correction term. Usually you would write in other statistics classes n-1. But in machine learning, people don't worry about sample variance, or sample statistics is usually all using the population equations for computing the population statistics. So in that way, it doesn't really matter because it's really more about mean centering and learning an normalization scheme rather than having something that is, let's say, correct in the context of statistics. Okay, where was I? Yeah, we compute the mean, the variance, and then we standardize our net inputs. So this again will result in net inputs centered at 0 with unit variance after the standardization. It's pretty much the same that we did for the inputs. So the axis, the network inputs, not the layer inputs. But I told you before, normalizing every hidden layer like this, or normalizing the net inputs like this at every hidden layer wouldn't be very useful. So, and this is why it's only step 1 of batch normalization. There's another step. And this is the second step 1 of batch normalization. There's another step. So, but before we go to step 2, one more note about a practical aspect of applying step 1, our standardization step. So one problem that may occur here is if you think about MNIST. So MNIST are again just some images that contain handwritten digits, and what's common across all these images is that they are centered. So all the relevant pixels are in the center of the image. So one problem with that is, for example, if we look at the position here in the left corner, it's always the same value. It's depending on whether we use normalized version or not, but it really doesn't matter. The value here is always the same. For example, it's a pixel value 0. And that may mean that also the variance will be 0 if it's the same value across all images in the mini batch. And then we will have a 0 variance, 0 standard deviation, and then divide by 0, which will cause a 0 or division by 0 error. That's not a valid operation. So to avoid this problem, what we do in practice is we add a small epsilon term here. It's a small constant like 0.00005, very small number to avoid dividing by 0, and that is just a very minor practical aspect. But now let's go to step 2. And this is the more interesting step about batch normalization. So here again, this is step 1, the standardization step. Here we are at step 2. This is our more interesting step. This is where we introduce now 2 learnable parameters. So one parameter is gamma and one parameter is beta. And these parameters scale our standardized net input. So here, this is our standardized net input, which you can find here again. We scale it by gamma, and then we add this beta parameter. And these parameters are learned by stochastic gradient descent. So we also learn them by computing the partial derivative of the loss function with respect to this gamma j here. And we do the same thing for the beta, similar to how we update the weights and biases. So also similar to, there's a z vector, and the vector z contains z prime 1, z prime 2, up to z prime, let's say h for the number of units in the hidden layer. And similarly for each of these we have a gamma parameter, and for each of these we have a beta parameter. So we would also have a vector for the whole hidden layer. We would have a vector gamma that would contain all these gamma values. So h is the number of hidden units. So 1, 2, 3, and so forth. So, and the same also for beta. I'm not drawing beta here, but you get the idea. So we introduce now 2 different new parameters for each hidden unit. So what it basically does is just, it scales back the normalized or standardized activation. So we applied some standardization here, and this gamma parameter allows us to scale it, to multiply it by, to make it larger by multiplying it by a number greater than 1, or shrinking it by multiplying it by a number smaller than 1. Also, we can have negative numbers, of course. Then we have a second parameter which controls the mean. So if you look at this, it's basically pretty much the opposite of what we just did in step 1 here, right? So step 1, step 2. As you can see, if I would just do this in reverse, what I would do is I would multiply by the standard deviation and then add the mean, so to undo this operation. And this appears to be exactly what the second step does, with the only exception that it's not that, or what could happen is, for example, it could be that gamma has exactly the same value as sigma, or standard deviation, and that beta has the same value as our mu, or sample mean. So if we have this condition, which will, by the way, be super unlikely in practice, but this would be just reversing the standardization. So what the network could learn technically is, by learning these parameters, is to undo the standardization procedure. So this is really like standardization, but it has more power because it applies standardization, but it gives the opportunity to do something more, but it also gives the opportunity to just ignore this standardization that we had. So if the network finds, okay, maybe it's good to just not standardize features at all, then it can technically learn that. So it's a learnable way of normalizing hidden layer inputs. Okay, that's actually what I just said. Yeah, sometimes I include notes. I don't, it's hard to speak and read at the same time. So I have usually notes here on my slides that I want to cover, but then I find I already talked about it. In either case, so this is just the general outline of how batch normalization works in 2 simple steps. It's maybe still a bit abstract how that looks like in a neural network. So I made a small graphic here to illustrate this. So this is, again, imagine the hidden layer, 2 hidden layers from our multi-layer perceptron. Let me go back a little bit. So imagine I have this network. So blue is my input, yellow is my first hidden layer, pink is my second hidden layer, green is my output layer. And I'm only, for simplicity, looking at one path here. I'm not looking all of them at once because it would be a little bit complicated. Okay, so this is the same network, but I'm again only looking at one path. And what I did is, in addition, I included the batch normalization layers now. So I have my network input, the x1 here, the first feature. Then I have my z. So it's my normal net input, which is computed by multiplying the weights with the features and then adding the bias. It's like the normal thing we usually do. Then we normalize or standardize these net inputs, get z prime. This is the first step of batch normalization. And then in the second step of batch normalization, we apply the additional parameters, the gamma scaling parameter and this beta mean parameter, which can add a constant that could be equal to the mean, but it is just, it's learned by differentiating the loss with respect to beta, so it can be any value. Then this is, so usually we call this or we can say that it's a scaled net input. This is usually called the pre-activation because it's done before computing the activation. And this is usually where we compute the activation. So in a neural network without batch normalization, how we computed the activation was we had a activation function, let's say a logistic sigmoid function, and the net input was the input to the activation function, and out came the activation value. Now what we have is we compute the activation by providing this pre-activation value to compute the activation. But then, like in a normal neural network, this activation A goes to the next layer. So the next layer again computes. So this is, let's say, Z1, and then Z2 would be again. So this is the weight at the second hidden layer. So let's put a 1 here, 2 here, times A1 plus B2. So again, we compute the net input as usual, and then we compute again the standardized net input in batch normalization, and we compute the pre-activation, and then again compute the activation, and so forth. So again, these, maybe I should make it more clear. These are batch normalization steps, and these are also batch norm. Or I should maybe say, sometimes I use the term batch normalization. This is like the official name of batch normalization, but in practice everyone says batch norm, or like here, this is like the very common abbreviation. So batch norm is just a short form for batch normalization. Okay. Yeah, one more note about this parameter beta. So when we compute the Z, the net input, we usually have the weighted inputs plus the bias unit. But if we have this beta, it really makes the bias redundant, because we are just adding a constant. And if we have this beta term, it's just like adding two constant. It's not really useful in that way. So we really don't need this beta value. Bias value here. So it's kind of redundant. If we build multi-layer perceptrons with batch norm, we usually don't use bias units because it's just wasteful, not useful. Okay, that is all I wanted to say, I think, about the individual steps of batch normalization. And next, let's talk about backpropagation for batch normalization. I told you once that I don't want to torture you with too much calculus anymore, but just to give you a brief overview of how backpropagation works for batch norm, I think this is generally just helpful to better understand what's going on in deep neural networks. So here on the left-hand side, I'm just showing you the familiar figure. I've shown you this figure of the multi-layer perceptron many times now, but just to recall the multivariable chain rule here. So what is going on here is we are interested in computing the derivative of the loss with respect to the first weight here, the first hidden layer. So this would be this one. So imagine we have this multi-layer perceptron with two hidden layers. So hidden layer, first hidden layer, and the second hidden layer. And the output here, there's just a single output, so this would be a network for binary classification. You can also think of this as A1, 3, the activation of the last layer, it's the output. And what we want to do is we want to compute the loss with respect to this one. In order to compute the loss with respect to this first weight, what we have to do is we have to trace the path, everything that is connected is connecting the loss with this weight. So if we do this, so we have loss, and let's circle the loss here, because the loss depends on the output and the true label. So we go back here. Then what we need is this part, A1, because A1 connects here, which then connects here. But also what we see is that there's another connection here that also goes here. So we have the parts that we need are these. Let me use a different color again. So this is what we need, and since we have two dependencies here, so one is A A12 and A22. And because to combine them, as you know from calculus, as we discussed earlier, we need the multivariable chain rule, which is simply here this second part that we add to it. So we have two parts, this one path, which, let me clear this for a second. Okay, then we have more space, gets crowded here. Okay, so this path, if I only look at the upper one, would resemble this one, because now what we have is the derivative of the loss with respect to O, the output, and then the derivative of the output with respect to the activation of the layer that comes before that. And then we go back further, and then we compute here the derivative, so that is, we are right now here, compute the derivative of this part with respect to this one, and then lastly this one with respect to this one. So this is the fourth term here. And the upper part would be this path that I've drawn, but since we have a second connection here, we also have to consider this path here. So the one that goes out from A22. And in order to compute this path, we just do the same exercise. We compute the derivative of the loss with respect to this one. And then this is, sorry, we are right now already here. And then we go, so it should be one more intermediate step. The derivative of the loss with respect to the output, the derivative of the output with respect to this A22, and then the derivative of this A22 with respect to A11, which is here, and then lastly the derivative of A11 with respect to W11, which is this part. We just simply add them up with a multi-variable chain rule. Okay, so that was just a quick refresher of how the chain rule works for a neural network, for a multi-layer neural network. So let me go back now and simplify the chain rule a little bit. So here we only have a single path, so I'm just considering a simpler case now. We will get back to the multivariable chain rule very soon, but now let's for a moment simplify this. So this is exactly what I've shown you on the previous slide, except that I'm only looking at one path now. So before I had multiple branches, I only have one branch now, without the other dependencies. So what I'm doing here is I'm showing you the same thing a little bit in more detail. So first we were only computing the derivative of the loss with respect to this one weight, but of course in a neural network we have multiple weights, or in general parameters. Another parameter would be the bias. So we need to compute multiple partial derivatives with respect to the parameters. So for example, to compute this one, we have this term. For this one, we have this term. And for this one, we have this term. And as you can see, of course, the derivatives become more involved, but there's also some recycling going on. This is nothing new. This is something we have talked about before. So when we have the partial derivative of the loss with respect to the output, go this step, and then this part, the derivative of the output with respect to the weight, is computing this part. So this would be combined the derivative with respect to the weight, to a weight in the last layer, last weight. But if we want to go back further, what we can do, or what we need is, we have to make a small change where we can recycle certain things. So what we can recycle, well, the second one is this part. So we can copy this over. However, now we are not interested anymore in this weight. We are interested in the one that I have in the green box here. So for the second derivative, I don't need this part. So what I do is I backpropagate here, and then here, then here. So this first part, this would be derivative with respect to the output, then the derivative of the output with respect to aj2, and then lastly this derivative is this part. So this is for the second weight, and then for the first weight here, for this one, we do the same thing. Now we can actually recycle two things. We can recycle these things and copy them over. So these are copied over. But again, I'm not interested in this one, so I have to jump one step further. So I go here, here, and then I go directly here, which is this part, and then from here to here, which is this part. Okay, so this is just, again, how simple backpropagation works. So the next slide, I'm slightly expanding this. So I was showing you only the activations in the previous slide. So now I'm also adding the net inputs, the Z's. So what I'm simply doing is I'm expanding this step, which is going from here to here, into two individual steps. So because remember, an activation can be computed by applying an activation function to Z, whereas Z is in turn computed by the weighted input. So this is, depending on where we are, this can be, well, let's write it like this, the activation of the previous layer. So I'm just expanding here. So from the partial derivative of the output with respect to the weights, this can be done in two steps. So the partial derivative of the output with respect to the Z, and then Z, the partial derivative of Z with respect to the weights. So for, usually this would be just if we have an equation like this, and if I compute the partial derivative of Z with respect to the weight, with respect to this one, so applying the simple calculus rules, this would be a constant, so this would actually cancel. And this is a multiplicative factor, so this would also, this wouldn't cancel, but this would become 1. And then the derivative of that would be x, for example. That is something you've seen before. So I'm doing this here, I'm just expanding this, and let's just say I would, because it was a little bit tedious just to write this and a little bit boring, assume I did the same thing here at the bottom. So I'm expanding these terms, and the reason why I'm doing that is because I'm adding now the batch norm steps. So what I'm doing now is, in between the activation, so we have this Z in between, in a normal neural network, and in batch norm we have these two new steps, where again, this is our standardization. And this is our, let's call this the scaling, learnable scaling step. So this is step 2 in batch norm, and this is step 1 in batch norm. So we have these additional new steps. I'm just repeating them here. This is nothing new. Again, here, these are the steps. We have seen them before. Okay, so what I was just doing is I was writing things step by step. So I'm just adding to this is a normal neural net layer, but I'm also only showing you one path. And in the bottom, I'm showing you the same path with these batch norm parameters added to it, or the batch norm operations. Batch norm, we have these two additional parameters, the gamma and the beta, for which we want to compute the derivatives. So we are also interested in the derivative of the loss with respect to either the gamma or the beta. And how we do this is, so we have these two additional steps, is simply we look at the chain rule again. So we have the loss with respect to A prime. A prime is the pre-activation in batch norm. And one thing to also notice that I is the index over the examples in the mini batch. So we have this sum on the mini batch. And because the batch norm parameters depend on the whole mini batch, not on a single training example. So you can't really have a sample size of 1 in a mini batch. I mean, you can technically, but wouldn't really make sense. Okay, so what we do here is we compute the derivative of the loss with respect to this pre-activation. So this would be here, this part. And then we have a beta parameter, for example, this one, which if we draw the weights here, let's say it sits here. Here sits a gamma and a beta. So in this connection. So to compute the derivative with respect to beta, which would be going back like this, it's pretty simple. We can just look at the beta here. So if we compute the derivative with respect to beta, all the other values are constant, so they would be canceling. And then beta would become 1, right? So this whole term becomes 1. So we can actually cancel this whole term such that the derivative of this part is simply the derivative of the loss with respect to this pre-activation here. Okay, that was pretty simple for beta. For gamma, this is maybe a little bit not that much more complicated. It's the same concept. Let me use a different color. So we go back from the loss, but now we go back here to pre-activation again, and then to this gamma. So the first term is again the loss with respect to the pre-activation, which is the same as here. And the second part is computing the derivative of this pre-activation with respect to gamma, which is this second part here. Yeah, this is also pretty simple. Let's look at the equation again. Gamma times z prime plus beta. So since we compute the derivative with respect to gamma, beta becomes a constant, so this goes away. Z is also constant, but yeah, remember from calculus, so this would be a multiplicative factor, so the z. So gamma becomes 1, so we have 1 times z prime, which is then basically the derivative of the second part. So this whole thing becomes just z prime. Yeah, so this is what I have here on the right side. So this simplifies to this part. So this would be the derivative with respect to gamma. Okay. There are a few more steps though, because we also have the standardization step where we have mu, the sample mean, and the sample variance, the sigma here. So we have two additional steps. And this is also then where again the multivariable chain rule comes into play, because we have to add them up. You can think of these steps as separate branches. It's similar to when I've drawn you the multi-layer perceptron exercise. So let's see what I've drawn here, or what I've written here. So we start again by the loss. Let's say we compute all of this in one step. So this would be the partial derivative of the loss with respect to this part. And then for the next part, we go back here. So this is the second step. This is the derivative of z prime with respect to just z. And we have to add this up with the mean, so the sample mean, because this is like a separate scaling step. So what we have is this part where we compute the derivative with respect to mu. Mu is here something that we estimate from the sample. And then, so the sample is the mini batch. And then we compute the derivative of the sample mean with respect to z. And we also add up the mu here, sigma here, sorry. So, yeah, one more thing I wanted to say in the previous slide. It's maybe a little bit confusing why we have to do this. So in the previous slide, what we did is we computed beta and gamma. So these are here the leaf nodes, the weight parameters that we want to update. But now we stopped, basically, we went back from, let me use the blue color here. We went from the loss to here, into here, but ultimately we also want to update our weight parameters, right? So we have to go back further. So in order to do that, so in order also to update the weight parameters, we also have to compute this whole term with respect to, so the loss with respect to z here. And this also involves mu and sigma, because this is scaling our activations. And this is actually not as complicated as you might think. So for computing, let's say that, so we can compute according to the multivariable chain rule. Since we add them up, we can all compute them separately. We don't have to do all at once. So if we do one at a time, so computing, let's say this part, the difficulty would basically be in this one. So the left part is something that is almost the same as what we've done in the previous slide here. So because instead of computing it with respect to this beta, we would compute it with respect to this z. So all that changes is, it's a little bit crowded here. Okay. All that changes is, so before we had beta and gamma, and all that changes is now we are going back to z prime. So before we computed it with respect to the gamma, for example. Now we can do the same thing for the z. So it's almost identical to this term. So before, so this term was this part. Now let's say we change this to, we are interested in z prime. So it's exactly the same, except now, so this is the same a prime, except now the derivative would be just gamma, right? Because this is a constant and this one will become 1. Okay, and similarly for, yeah, this is it basically. So a part of the computation of this part in the previous slide. I mean, we won't go over the whole derivation of this term here. We don't want to cover everything because it would take maybe too much time, but let's just look at a few more terms in this partial derivative, how we can compute it. So one term would be, for example, this one. This is the partial derivative of z prime with respect to z. And again, z prime, this is our standardized net input. This is just z minus the mean divided by the standard deviation. And so in order to compute the derivative of that, I mean, this is pretty simple. If I want to compute z prime with respect to z, what I just do here is I take a look at all the variables here. So mu and sigma, they will become constants. So maybe let me rewrite this as let's write it as z minus mu times 1 over sigma. Then it's maybe easier to see. Mu becomes a constant, so this goes away. Z, so also one thing to say here, this is one single training example. So for this part, we're only looking at one training example at a time. Okay, so for mu, this becomes a constant. Z becomes 1. And then what's left is basically 1 sigma times 1, right? So 1 sigma, this is a factor here that we multiply by. So we have the derivative. The derivative stays like that. I mean, like, you know, from calculus, if I have something like ax and take the derivative of that, where x is my variable, the result is basically a. So that's what was going on there. Okay, so we have derived this first term here. So let's maybe do this one here as well. So this one is the derivative of the mean with respect to z. So again, we are only looking at one example here. So the mean is computed over the mini batch. So we have, say, this, and then all the zi's. But I'm only looking at one single example here. So there is no sum. And again, in calculus, because we compute the derivative of mu with respect to z, the derivative, we only have one variable here, so the derivative of this one will become 1. So what leaves us, like before, is only the 1 over n term, which I have put here. Okay, one more maybe. So this one, the derivative of the variance with respect to the net input. So the variance would be 1 over n sigma, and then we have this squared term. So we have the net input minus mu squared. Yeah, and this is again only for one single example, so there won't be any sum. And again, what we do is here we apply now the power rule in calculus, so we bring the 2 forward. So it is simply 2 over n times z minus mu. Okay, so the inner times the outer derivative. So yeah, this is about it. Yeah, so the inner derivative, because we use the chain rule, there's an outer term and an inner term. So the inner derivative would be simply 1 minus 0. So we multiply this one thing times 1 minus 0. But this is just 1, so we can also just get rid of this. Okay, that's this term. There are a few more terms. I don't want to go through this too much because I think it's already a pretty long lecture and we just covered only batch norm so far. So there are more terms. If you like math and engineering, like I always think of calculus as something I do in engineering, you can maybe solve for the other terms as an ungraded homework exercise. You don't have to, I won't ask you that on the exam, but just if you want to understand batch norm better, you can maybe also take a look at these terms. So I've already done most of this one, and you can, I mean, these are pretty relatively simple. So you can at home, if you like, to work on these, but you don't have to. So one more thing about batch norm is how do we actually use that in practice? So in PyTorch, for example. So PyTorch already implements batch norm. We don't have to do this ourselves. So what we simply do is we add a batch norm layer after each hidden layer. So if we have a hidden layer, we simply add a batch norm layer after that. So I'm applying, I'm applying that here. No, not really. Here. So this is the equivalent of that. And also what I want to say is in the classic paper, in the first batch norm paper, the batch norm comes before the activation. So we apply batch norm and then we apply the activation function. So this is also the same as we talked about in the slides, in the previous slides today. What else? Yeah, there's a 1D here. This is assuming here a multi-layer perceptron. So each unit is independent and we have some, so our inputs are a vector. But if we later work with images, for example, later we will have, let's say, our MNIST images, and we don't reshape them into a vector. Remember in multi-layer perceptrons, what we did is we concatenated each row to a long vector. So if this is my row 1, 2, 3, 4, 5, 6, what I did is I made this very long vector. 1, 2, 3, 4, 5, 6. So I just reshaped or concatenated each vector to each row to a very long vector. So in that way, each pixel in the image has its own gamma and beta. So this is because it's a vector, that's why the 1D is here. Because later we will talk about other architectures where we don't need to create these vectors, where we can directly process an image as a matrix. Also each layer in the image would be a matrix, and if we have multiple color channels, we would have a 3D tensor. And there will be a method that is called batch norm 2D, which does not assume that we have reshaped this into a vector. But ignore this for now. We will come back to this after we talked about convolutional networks. But remember just to put the 1D here if you work with multi-layer perceptrons. And this is about it. Of course, you can also use the sequential API. So you could also do the, so instead of having everything in the forward, you can also have in the init the torch.nn.sequential, and then have torch.nn.linear with your values, and then torch.nn.batch norm 1D, and then your, I don't have space here, but then your parameters. You can also put everything in the sequential API, of course. Yeah, also there's one parameter for batch norm here. That's the number of hidden units. So again, why we need that is because the number of batch norm parameters depends on the number of units in the hidden layer, right? Because each activate or each net input will have its own gamma. This is, I think, all I can say about this here, about the code. It's pretty straightforward. One thing just to remind you though is, like we said for batch norm, for dropout in the last lecture, in dropout we emphasized that we need this model.train and model.eval when we use batch norm. So why do we need that? So again, this is in the training loop, similar to dropout. So I don't have code example of the training loop here, but it is identical to what we did in dropout. Because the reason why we need model.train and model.eval again is because batch norm behaves differently during training and during testing. So during training, we get the mean and the sigma from the mini batch, right? So we compute this from the mini batch. So in testing or in inference, as we call it in machine learning, in deep learning, so inference, always put this in quotation marks because it's a little bit of an awkward term for referring to classification or testing. Let's say testing or just predictions. So if I, let's say, finished training, I want to use my model for predictions, I may not have a mini batch, right? So imagine you are Google, you have your deep learning model for doing a language translation or predicting, let's say, or just returning search results. You have maybe one customer. So the one customer, you want to give the customer your prediction. You don't want to wait until you have a mini batch of 32 customers before you do your prediction, right? So for Google, for example, if you have your customers, you want to process them one by one, you don't want to wait until you have always a mini batch size full of customers before you do some computation. So what that means is if we only have one data point during testing or prediction, we can't really compute the mean and sigma from that one data point, right? So we have to do something in addition to that. So we have to somehow save the mean or sigma that we can then use during testing. And there are two ways to do that. So the first way is just to keep a running mean. That means that during training, we compute this running mean, and we do also the same thing for the variance. We have a momentum term, the 0.1 here, and we'll multiply. So this is the current running mean. So we multiply the running mean with a momentum term, which is usually 0.1. And then we add to this 1 minus the momentum term, which then would be 0.9, times the current sample mean. So this is based on the current mini batch. And this is, we keep this running mean during training, so we update it. And this is simply just an exponentially weighted average or a moving average. You have probably worked with that, for example, if you worked with time series and things like that. So we just keep this running mean in the background during training, and then when it comes to the testing, we just use this running mean instead of a mini batch mean. And alternatively, so this is one way to do this. A second way would be to use global training set mean and variance. That means simply that you compute the mean on the whole training set and the variance on the whole training set, and then keep these parameters. This is another way to do this, and both are equally fine, I would say. In practice, this one is more common. I think it's just because it's more efficient. You don't have to compute something on the whole training set, because sometimes you have to change your code because you usually can't load your whole data set into memory. So you have to write some extra code to compute the mean and variance, so you have to load each data point at a time. I mean, it's actually not much work, but I think it's just slightly more convenient to do version 1. And this is also what's going on in PyTorch. So by default, when you use PyTorch during testing, when your model is in this eval mode, it will use the running statistics. So it will keep the running mean during training and then apply it during testing. Okay, that is maybe all I wanted to say about the basics of BatchNorm. So next, let's maybe talk about why BatchNorm works. I just gave you the mechanics, but why does it work so well? Actually, it's not really clear yet how or why batch normalization works so well in practice. There are multiple opinions. So the first is the original paper. So the original paper that proposed BatchNorm suggests or hypothesizes that it helps by reducing internal covariate shift. And internal covariate shift, this is again another jargon term in deep learning. Here this means simply that the features shift or change during training in the hidden layers. So during training, there are changes in the distribution of the different features. But there are also other papers debating that this is really why batch normalization helps. So it's a little bit controversial. And in my opinion, I mean, this is just an opinion, but in my opinion, batch normalization just adds additional parameters to the network. So we have these gamma and beta parameters that we add. So it just has, I would say maybe it produces a network that has higher capacity. So there was also a recent paper, I forgot the name, but if you really want to see that, I can maybe find this again. So in this paper, what the researchers did is they froze all the weights in a neural network. So let's assume they had a neural network where you had, so actually they used convolutional networks, but doesn't really matter here. So they left all the connections like they were in the beginning. So all the weight parameters were kept constants. They were randomly initialized like always, but they were not trained. And they only trained the batch norm parameters. And they found that by only training batch norm, you can already get a pretty good performance. So in that way, a network that only learns from the data by updating the batch norm parameters is already capable of doing good classification. So maybe batch norm just helps because we have more parameters. There would be an easy way to test this actually by just increasing the number of parameters in the network without, let's say, not using exactly batch norm, but using some other scheme and see whether that helps. Another paper that was, so the original paper was from 2015. A more recent paper from 2019 was this one, where people or the researchers looked again at different aspects of batch norm and tried to find out why it works so well. And they found that the distributional stability of layer inputs has little to do with the success of batch norm. So they hypothesize that why batch norm works is not really due to preventing the internal covariate shift, but it is maybe more due to something else. And they found that, or they hypothesized that this is mainly due to making the optimization landscape smoother. So it just added some figures from this paper where I'm just showing you some of the results. And one conclusion was that it's the same paper, that a batch norm enables a faster convergence by allowing larger learning rates. So what we see here in this figure from the paper is in the red ones, or the dark orange ones here, if we look at these, are the regular neural networks without batch norm. So standard means just a neural network without batch norm. And there are two learning rates, learning rate 0.1 and learning rate 0.5. And they see that if you use a learning rate that is too large, here 0.5, you get a very poor performance. So this is the training accuracy on the y-axis, and here they did the same thing for the test accuracy. So you can see for both training and testing, if you use a learning rate of 0.5 without batch norm, then this network doesn't really train very well. So this is a learning rate that is too large. There was actually, now that I think back of this, a question on Piazza either yesterday or 2 days ago, where a student asked about a network that didn't learn, and this may be due to not good learning rate choice. So if your network looks fine, there's no error in your code, and it still doesn't learn, then usually or often it's the learning rate that is maybe too large or too small. But so back to this figure. So what they found though is when they use batch norm, so in blue, the graphs in blue are the ones with batch norm. They found that with batch norm, they first of all get a higher performance or higher training and test accuracy when they use learning rate 0.1 compared to the red line. But at the same time, it also allows the network to train with a higher learning rate. You can see that here. So in that way, networks with batch norm are more robust to bad learning rate choices or they can cope with large learning rates. But you can see this one is maybe not as doesn't train as fast as this one, but there's something going on that in the end, the performance is almost the same. So here, again, the smaller learning rate is maybe better, but still batch norm allows us to use larger learning rates, which is maybe nice. So although it may not give you the same performance as here, you can already see that a large learning rate is not too terrible here. Okay, so that was one takeaway. You can use larger learning rates when you use batch norm. And the other big takeaway was that they hypothesized, or based on this experimental evidence, that the good performance of batch norm doesn't seem to be directly related to preventing the covariate shift. So what they did is they investigated 3 settings again. One is the standard one without batch norm. One is a network with added batch norm. And one is this noisy batch norm where they added some distributional instability. And what we can see here is that, so this is the standard one, and in the center, this is the standard one plus batch norm. You can see there's less covariate shift going on, so the distribution is more, I would say, constant here. But at the same time, so on the right-hand side, they have batch norm and add some noise to it. So here they again have internal covariate shift going on here. And still, even though there is internal covariate shift, they find that there's still good performance. So you can see that here. The performance, even though there is some noise added, is better than the standard one without noise. So maybe the internal covariate shift is not really why the network learns better. Okay, batch norm prevents internal covariate shift, but this may not be the reason why it works so well. I was just looking or summarizing some literature about batch norm. I mean, I use batch norm, but I'm not like, I don't do research on batch norm, but I just find it interesting to sometimes look what people think about it, because it's a very commonly used technique and there's this ever ongoing debate on why it works so well. So the first paper mentioned that it may work well because it prevents this internal covariate shift or reduces it. Then this 2018 paper I just showed you showed that batch or new networks can already train well even if there is internal covariate shift. So batch norm may work well, but whether there is internal covariate shift or not doesn't really matter, depending or based on the performance that they found, that it doesn't really matter that much. So the hypothesis is that batch norm works so well because the optimization landscape may be smoother. Another paper from 2018 that did research into batch normalization, trying to understand it, found that batch normalization implicitly discourages single direction reliance. What that means is that, like they said, that the inputs to a layer have, so single direction reliance means that a single input influences only a single unit or a linear combination of units in the next layer. So this is similar to what we talked about in Dropout, that the network, there's, let's say, a one-by-one correspondence between two layers. So we sometimes depend on single individual units. And this paper found that when we use batch normalization, it discourages neural networks to rely on single inputs, that it considers more inputs. In that way, it's more like, in a way, like somewhat related to what Dropout tries to achieve, that we try to rely on multiple inputs. So another 2018 paper found that, or hypothesizes that batch norm acts as an implicit regularizer, and it improves generalization accuracy. So it is here understood as, or can be regarded as, a regularization technique. And another more recent paper, 2019, found that batch norm actually causes exploding gradients. I think before I mentioned that batch norm may help, or clever initialization and normalization may help preventing exploding and vanishing gradients. Maybe here this suggests that it maybe even causes exploding gradients. And it requires careful tuning when we train neural networks without skip connections. And skip connection networks are, for example, the ResNet, the residual neural networks, and we will talk more about this in the CNN lecture. So we will revisit skip connections later. This is just a brief summary of what people think batch norm is doing. Of course, I mean, there are many competing theories, and I don't think we have a conclusion yet, so why batch norm works so well. Like I said, my opinion is just it's additional parameters, and that may help, but who knows, maybe we'll see some more papers this year. Okay, with batch norms, some minor practical considerations. So as we've seen in the previous slides, the original paper proposed putting batch norm after the layer that computes the net inputs. So if you think of it as a PyTorch approach, after applied linear and before we apply the activation function, for example, our ReLU function. So this is how we usually apply batch norm. We add it after we computed the linear the net inputs, and then batch norm we call it also as computing, or it was a method for computing the pre-activation. That was before we applied the activation function. Again, the two steps. One, so for the pre-activation was standardizing, and two was the scaling by using gamma and beta, the two parameters. So some people think, not sure exactly why, but some people think it makes more sense to add the batch norm after we apply the activation function. And then maybe, for example, this gives me the network an opportunity to also learn mean-centered inputs to the next layer, because if you think about ReLU, so if I have a ReLU function like this, it will cut off all the negative values. So in a way, even though we applied the scaling and batch norm on this side here, we'll always have only positive values that go into the next layer. So maybe people think it's useful to apply batch normalization after we apply the activation function. But yeah, again, this is just one way to do it. And in practice, though, people sometimes find this performs better. So I was looking for some benchmarks, and I found this website here, CafeNet benchmark. Caffe is a very old deep neural network library. I mean, not so old, but in terms of how fast the field evolves, Caffe is old. Here the researchers, the researchers did some comparisons. I'm actually not sure exactly what this plus, scale, and bias means. So let's just assume let's maybe just assume this one and this one are the regular batch norm approaches. And this one, like I said before, the before is the approach here on the left-hand side, where batch norm is applied before the activation function. And the other one is applying batch norm afterwards. And they found here that applying it before results in a better accuracy than applying it after. So here from a practical perspective, it may be beneficial to apply batch norm after the activation. Here it's an overview, the same website. Here's an overview of different activation functions combined with batch norm. And here I would say the conclusion is simply that batch norm performs well with a whole selection of different activation functions. And because we just talked about dropout last lecture, I thought this is interesting. We can also combine batch norm with dropout. So what they did here is they had a combination of batch norm and dropout. And also what was interesting is that adding dropout makes it perform even better, so compared to no dropout. And also interestingly is adding too much dropout, 0.5, also again results in a lower accuracy. And this is maybe what you also will observe in homework 3, that if you make the dropout too strong, you will reduce the overfitting, so the difference between training and testing, but overall your performance will also suffer. So if I have the number of epochs and my loss, and let's say this is my training accuracy, and this is my test accuracy. It shouldn't be that low, but it doesn't matter. What I'm just trying to show you is this difference here between training and test. So let's say without dropout, we have this overfitting going on. Now if I add dropout, I may reduce the overfitting. So let me just make this in dotted now. So now after I apply dropout, I may reduce the overfitting, but I may have something like, doesn't it dot here? I have now training accuracy like that and test accuracy like that. So I have reduced the overfitting gap here. It's a little bit smaller than before, but maybe I've dragged down both the training and test accuracy. So this is why even though dropout may reduce the overfitting, it also can result in an overall lower test performance if it's too much dropout. Another last aspect about batch norm is that in a recent paper, or not that recent, but also again 2018 by Keming He and his colleague Wu, they found that adding, or it's also generally known that adding or having mini batch sizes that are too small are not beneficial for batch norm. So if you use batch norm, you want to have a sufficiently large mini batch size, and it should be at least 32. So here their limit was 32, but usually 32, 64, 128, 256, and so forth. Good batch sizes for batch norm. You don't want to go smaller than 32, because then your performance will decline. So here in this plot they show the error, and the error for batch norm, the batch norm is the blue graph. They show that the error goes up the smaller my batch size becomes. So here's the batch size of 2. This is a batch size of 32. So 16 may still work well here, but I think when I remember correctly from another paper, the recommendation is generally 32. If you go smaller than 32, usually you find that you get poorer performance. And that is of course because your mean and standard deviation are computed for the mini batch. So if it's too small, then it's too noisy. So the mean and variance will be too noisy if you just use very, very small batches. So related to that paper, I think I mentioned that in the very first slide there are other related techniques related to batch norm. I just want to briefly cover this. We may revisit this when we talk about CNNs. So there are three other techniques: layer norm, instance norm, and group norm. And this figure is taken from the group norm paper by Keming He and Wu. And here, what we see is just a comparison based on a batch of images. So we will, again, this is maybe a little bit confusing since we have not covered convolutional neural networks yet, but you can think of this as a 3D tensor for images, whereas n is the dimension for the training examples and training examples in the mini batch. So n is the number of examples. C is the number of channels. in an image, for example, RGB, like 3 color channels in an image, and H and W are the height and width. So here what they are showing is how, or they are comparing how the different methods work. So in batch norm, this would be the batch norm 2D actually, that we will talk about when we talk about CNNs. We compute the mean and the standard deviation or variance over the whole mini batch for one channel. So in 2D, batch norm 2D, we'll compute this on a channel basis. Before, in the multilayer perceptron, we do this on a feature basis. And here we do it on a channel basis. So each mu j, the mean j, and the sigma j, and correspondingly also the gamma j and the beta j are computed for each channel. So we have channels, let's say, yeah, up to C. So 1 to C. So j is an element of the channel index. Okay, so this is how batch norm works. We compute this for each mini batch for each channel, and in layer norm, what we do is we compute parameters based on all channels at once, but only for one training example. So n here is only one training example because we only look at one column here. So blue again is the part from which we compute parameters, and there's a kind of special case, instance norm, where the computation only happens per channel and per training example. So this is very extreme, and there's a middle ground. This is group norm. This is what this paper is about. So in group normalization, they have some, I would say, some special case between, or some hybrid between layer norm and instance norm. So here they compute this, or the parameters, based on half of the channels. Okay, so these are just some other methods for normalizing hidden layer activations. But again, batch norm is still, I would say, state of the art. That is what most people use. Because I've heard, or you asked me this question a couple of times, why do I always say the mini batch size is 16, 32, 64? Why is it always powers of 2? So, I mean, it's like a tradition in deep learning. Back in the day, it was a little bit, we wanted to utilize our hardware as best as possible. And it has something to do with how many cores we have on a GPU. They are also, the cores on a GPU are also powers of 2. So for instance, like we talked about many times, using linear algebra operations helps us utilizing or parallelizing operations. For example, writing vectorized code helps us to compute things in parallel, which makes it faster. For example, using the single instruction multiple data paradigm, where we have the same instruction, we have multiple inputs, and each instruction and input gets mapped to a different core, for example. For instance, if we have a matrix with 48 columns, we can compute each column or each dot product in parallel. So we can, for example, map 3 dot products to each processing core if we have 16 processing cores. So we usually, because the cores are powers of 2, we usually use mini batches as a size of 2, as power of 2, sorry. So this way it's traditionally easier to utilize your GPU. But of course, this is not, I mean, this is just kind of archaic. Nowadays, there are some cores that do something else on your GPU. So in that way, you won't really benefit that much. You can also, I don't know, choose uneven batch sizes, will be fine. Okay, so just to finish up with batch norm, a reading assignment that is somewhat optional, because most of this I talked about in this lecture. There's this original paper that proposed batch normalization. It's basically a more, I would say, verbose version of what I talked about in this lecture. So this is a good reference if you're interested in that, or actually should be interested in that, because batch normalization may be a topic in the final exam. Okay, so let me take a short break though to make a cut here. So I will upload what I have right now because I think it's already long, and I maybe need some water here. So let me make a short break here, upload this video, and then I will record part 2, the lecture about weight initialization. So we covered input normalization. Now we will talk about weight initialization.